Hi, can you hear me?
Yes, sir.
Okay. So before beginning, there is some update about the format of the next exam. I don't know if you got a chance to look at the updated rules, but I'll post the link on our WhatsApp group. Basically, now there will be only one exam which has both sections of pre-RMO, that is IOQM, as well as INMO, Part A and Part B. So basically, in the same paper, you will be attempting both numerical as well as long form subjective questions. So you need to be prepared for both exams. And I mean, the most important thing is they are both of the different formats. So the expectations of what you need to do is slightly different in each case. In the case of the numerical format, the most important thing is you want to finish as many questions as possible as accurately. The method doesn't matter. I mean, getting to the answer is the most important thing, and getting to the answer accurately. Whereas in the subjective format, the what you are thinking, how you are presenting your solution, all of those things matter. So I mean, almost like we have to switch gears in between the exam. It might be quite a challenging exam in that sense, just because of the format. But unfortunately, because of the way the COVID pandemic has turned out, we don't have enough time to conduct two stages. So that is why we have to come up with a solution like this. So in any case, I mean, just go through the rules and be prepared for that. The exam is on 6th March, as far as I know. So I mean, yeah, so 6th March, I think morning time, so 9 to 12. Let me check. But so we have after today we have 3 more Sundays to up to the exam. So just as before the IOQM, I had given you one practice paper of IOQM style. If I'm able to set a question paper of this new format in time, I would like to share that with you also. So, I mean, even if we are not able to conduct the exam online, I'll just give you the question paper so then you can time it and solve it yourself. At least let's try to do that. Okay, so I'll share the paper on WhatsApp. But yeah, in general, just be prepared for this exam format. And so, I mean, the focus of your studies in the next few weeks should be on both kinds of topics. So it should be somewhat easier topics, I would say, like combinatorics, counting, those kinds of things. But because there is a subjective section which might have harder problems in combinatorics, like pigeonhole principle and the things that we have covered related to that. So you need to study both as well. And I mean, as I see the rules, the way it is going to be graded is the first numerical section will be used to sort of filter out the top few students from every region. So so only those students, the papers will be checked for the subjective section. So it's not like everybody's subjective section will be checked. But if you are planning to aim for that top few students in the region, then you definitely have to do well on the subjective section as well. Okay. So I think probably the most important thing you need to do after the first section is over, once you have finished solving part A, and before you start solving part B, you just have to sort of reset your mind. That might be the hardest challenge that you need to work on. That whatever happens in part A, good or bad, you need to attempt part B with a fresh memory, fresh mindset, and most importantly, you sort of need to regain your energy for the next part. So make sure to take a sort of mental break before you start part B. Okay? So all of those things are going to matter a lot. But anyway, after all, whatever is the format of the paper, finally they're going to ask the questions which are related to the same Olympiad syllabus. So as far as our preparation in the lecture goes, nothing much has to change. So we will continue to do the topics that we had planned before. But as I said, just for practice, we will have one paper of that format. Okay. If you have any technical difficulties or queries related to the new rules, just let me know. I will get any doubts resolved from the coordinators. Okay. Okay. So yeah, last time we were looking at complex numbers, a few more properties of barycentric coordinates and things like that. So honestly, this is a very vast topic, barycentric coordinates or complex numbers in general. So I don't want to spend too much time on that. I'll just indicate one book for you to refer more advanced properties. It is by Ivan Chen. So I think Ivan Chen is one of the most active contributors to a lot of Olympiad material. So you might already be knowing his name. But in particular, he also has published a document of sorts, which has a lot of these. At the top level, it gives you all the sort of toolkit you need to know for barycentric coordinates in Olympiads. So it's a good collection to look at. So it is barycentric coordinates in Olympiad geometry. Okay, so like a 40-page book, and it covers everything that we are talking about and a lot more. So I just leave for you to refer to this book, but I'll just indicate one more point which I started last time in complex numbers. So that will be the last point we will to cover in this barycentric coordinates. So that was related to isogonal conjugates. Okay. So last time I mentioned about isogonal conjugates and particularly trigonometric Sevas theorem. So I'm not sure if everybody was able to recall those details, but we had covered those in the one of the lectures related to cross ratio. So if you go back to the lecture notes, I think you'll find. So one of the important things is that you need to revise regularly. So this is something which I tell always every year, that because we have limited time, we will not able to go back and revisit the topics we have done already. But it is our responsibility to make sure that everything is fresh in your mind the closer you come to the exam. So like this cross ratio topic when we had covered, I had indicated is trigonometric Sevas and Menelaus theorem, which we can easily derive from the normal Sevas and Menelaus theorem using this important property that VD upon DC, how you can convert ratios of sides or segments into ratio of the angles, sine of the angles. Okay, so just go back and revise these things. And the recommendation I would give you how you're supposed to revise this. Just going back and reading everything will take up too much time, and it's not that fruitful. What you need to do is you need to create your own précis or summary of the topic. So every topic that you revisit, or in fact while you do it the first time itself, you should try to summarize the most important points in some kind of like memory sheet, you can say. And so just reading that memory sheet should be able to recall all the details of that topic, and so that will speed up your time you take to revise, and also give you sort of a quick high level overview. Okay, so do that for every topic that you're studying, so that you can quickly revise and sort of stay up to date with all the topics, all the topics that you have learned. Because like one of the things is that lot of cross connections are there in your topics within themselves, and you would only realize those if everything is fresh in your mind. Okay, so for all of those reasons, I would recommend you to go back and revise these things. But anyway, just I want to elaborate on the isogonal conjugates part of it. Okay, because the connections of isogonal conjugates and barycentric coordinates are quite interesting. So let us look at that. So just to formally define what do we mean by isogonal conjugates. So if I have a triangle You can see my screen, right?
Yes, sir.
So if I have a point P, okay. So then by trigonometric Sevas theorem, what we can say is if I call this angles alpha 1, alpha 2, beta 1, beta 2, and gamma 1, gamma 2. Then this product of the sine alpha 1 upon sine alpha 2, this whole product will be 1. And for any point for which this product is, I mean, if there are any three rays from ABC for which this product is 1, then those three rays will be concurrent at some point. Okay. So the important observation is that if I take the reciprocal of all the terms, okay, so instead of sine alpha 1 upon alpha 2, if I took sine alpha 2 upon sine alpha 1, etc., okay, beta 2 upon beta 1, and gamma 2 upon gamma 1, then also if this product is equal to 1, then this product will also be equal to 1. So what that means is that here I considered these three rays, okay. So if I take the mirror image of each of these rays in the angle bisector, which means that here the order is alpha 1 and alpha 2. Suppose I take a different ray for which the order of angles is alpha 2 followed by alpha 1. Okay. And if I do the same thing on all the three vertices, okay, then I'll get three new rays. And for those three rays, the expression of trigonometric Sevas theorem is this second one. And because that product is equal to 1, what follows is that by the converse of that trigonometric Sevas theorem, that these three rays have to be concurrent. Okay. So basically, starting from one point in the triangle P, I'm able to obtain another point Q. Okay. So therefore, in this case, P and Q are called isogonal conjugates of each other. Okay, and we'll study some more properties of isogonal conjugates, but just to indicate the same thing can be done in normal Sevas theorem also. So here the reason why we took so we reflected every point in the angle bisector, right? So the reason for that is because we wanted to flip the alpha to alpha 1 angles. But in normal Sevas theorem, when we are considering the ratios on the sides, okay. So if I have some concurrent lines like this, okay, then ordinarily by Sevas theorem, we say BD upon DC, this product is equal to 1. So I wanted to, if I want to do the same thing over here, what I want is that suppose instead of point D, I consider a new point D dash where this ratio is flipped. So instead of basically I want BD dash upon D dash C to be equal to reciprocal of BD upon DC. Okay, and so basically if I take the mirror image of D in the midpoint, so this diagram a bit. In this case, the midpoint ends are very close, but anyways. So, but if I do the same thing on all the three sides, so in each case, I consider the reflection in the midpoint. Okay. So basically, what will happen is that this AE is congruent to CE dash, right? And this EC is congruent to AE dash. So therefore, what we get is CE upon EA, the original ratio, will be the reciprocal, or rather the new ratio, CE dash upon E dash A is the reciprocal of CE upon EA. And the same thing will happen on all three sides. So again, the what we'll get is this AD dash, BE dash, and CF dash, they will be concurrent again. Okay, so again from point P, I got a new point Q, but with a different recipe. So the point Q I'm obtaining here and the point Q I'm obtaining in the first case will not be the same because the procedure is different. But so again, these 2 points are, so let me call it some other name for now. We call it R. So then P and R are called, so the name for this isotomic conjugates. Okay. So just keep these two terms in mind, isogonal and isotomic conjugates. Okay. So basically, these are two different ways of, if you start with one concurrency, how do I get one more concurrency? So this could be useful in some cases. Okay. So is there a point which is its own isotomic conjugate?
So the midpoint.
Sorry, can you speak aloud?
So the midpoint.
Midpoint. So the centroid basically. So if P is the centroid, then DF are the midpoints. So the reflection of DF will be the same points. So therefore G is its own isotopic conjugate. Okay, and what about isogonal conjugates? Is there any point?
It lies on the angle bisector.
Angle bisector. So basically all the incenter and excenters, they are all their own isogonal conjugates. Okay. So all these 4 points are going to be their own isogonal conjugates. Okay, so these isogonal conjugates have few more interesting properties which we can check. There is one more well-known example of isogonal conjugates, which is the orthocenter and circumcenter. Okay, so orthocenter and circumcenter and orthocenter are also isogonal conjugates, and this I think we have already seen before. Basically, the only reason why that happens is that if I consider the line AO and AH, you will see that basically this angle is both 90 minus b. This is also 90 minus b, and this is also 90 minus b. So these AH and A are symmetric with respect to the angle bisector. Therefore, they are isogonal conjugates. In general, if you have any two isogonal conjugates, what happens is and we will see the connection with barycentric coordinates soon. But just in terms of pure geometry, I want to indicate some properties. Maybe you already know this, but just to be on the safe side, I am telling you. So if the isogonal conjugate of this point is Q, okay. So let us draw altitudes from P and Q to the three sides. Okay. Okay. So and let us give these points some systematic names. Let's say P1, P2, P3. Okay. Now, by virtue of the fact that they are isogonal conjugates, we can deduce some properties. So let us focus on, let's say, the point B. So from point B, the ray BP and BQ, because they are mirror images from with respect to the angle bisector. So therefore, these angles, if I call this angle beta 1 and beta 2, let us say this angle is beta 1 and this is beta 2. Okay. So then the reverse will be this. So this angle will be beta 2 and this angle will be beta 1. Okay. So from this, can you deduce that these 4 points are concyclic? P1, Q1, P3, Q3 are concyclic. Do you already see how to do this? If you so, just raise your hand. Okay, if not, I'll give you a few minutes to try this. Okay, so how do we see the concyclic points? we can use the power of B with respect to these 4 points. So if I prove that BP1 into BQ1, so it's enough to prove that BP1 into BQ1 is equal to BP3 into BQ3. Do you agree?
Yes.
And this should directly follow from the fact that I just use the cos of these beta 1, beta 2 angles, right? Because what happens? BP1 is nothing but BP cos beta 1 and BQ1 is BQ into cos beta 2. And the reverse will be true for these 2 points, right? BP3 is BP cos beta 3 cos of beta 2 and BQ3 is BQ cos beta 1. So when I multiply them, basically both sides will have one copy of BP and BQ as well as cos beta 1, cos beta 2. So therefore this will be true. Okay, so P1, Q1, P3, Q3 are consecutive. And by symmetry, do you see that all the other pairs will also be consecutive? So similarly, what I can say that P1, Q1, P2, Q2 is also consecutive. Well, there should be comma because these 4 points are consecutive. Just as a small point, when in terms of notation, when I say 4 points, they are consecutive. But if I write them without the comma, then I'm talking about quadrilateral. So in that case, I should say, suppose I omitted the commas, then the correct statement would be that P1, Q1, P3, Q3 is a cyclic quadrilateral. In terms of mathematical implication, it's the same thing, but just for notation, I'm saying that when I use the word concyclic, I'm talking about points, and when I say something is cyclic, I'm talking about a quadrilateral. So here, same way I can say P1, Q1, P2, Q2 are concyclic points, and what is the remaining pair? P2, Q2, and P3, Q3. They are also concyclic. Okay, so all of these 6 points, right? P1, Q2, P2, Q2, and P3, Q3. So if I take them 4 at a time, they are consecutive. Does that mean that there is a circle which passes through all 6 points?
No.
So we cannot directly say that. So this is a mistake which some students might make. That just because the points are pairwise consecutive, therefore you may think that there will be a circle passing through all 6 points. So it is true that there is a circle passing through all 6 points, but to prove that, you need to do something more. Okay, it's not enough to say that because the pair points are consecutive 2 at a time, therefore that circle will be common. So what can we do to prove that the circle will be common also? Okay, but I hope you understand this point. That in general, I could have 6 points such that there is a circle passing through the first 4. There could be a circle passing through the first 4. There could be a different circle passing through these 4 and a different circle passing through these 4. So there is no reason why all the 6 have to lie on the same circle in general. But something special happens in this case, because of which there is a common circle which passes through all the 6 points. So what is that special thing?
We can consider the midpoint of PQ and prove that it is the center.
Correct. So as it happens, whatever circle passes through P1 and Q1, so which means P1, Q1 is a chord of that circle. So if I consider the perpendicular bisector of P1, Q1, okay. So if I take the midpoint of PQ, let me call that point N. So the perpendicular bisector of P1, Q1 will also pass through N, right? Because these are just 3 parallel lines. And the same thing will be true from any other pair of points, let's say P2, Q2. So from P2, Q2 also, if I consider this perpendicular bisector, that will also pass through N. So the whatever circle passes through P1, Q1 and P2, Q2, the center of that circle is supposed to be at N, right? Because the 2 chords which we are considering, their bisectors are meeting at N. So therefore, basically what means that n is the midpoint of, n is the center of the circle P1, Q1, P2, Q2. And in the same way, n will also be the center of the other circles also, P2, Q2, P3, Q3, and P1, Q1, P3, Q3. So all the three circles have the common center n, and therefore what will happen is that the n is equidistant from all the 6 points. Okay, so therefore n is equidistant from all 6 points, and therefore n is the center of the common circle. Therefore, there exists a circle centered at n, passing through all the 6 points. Okay, so just appreciate this fine sort of reason that you have to do here. Okay, so this is quite interesting that whenever you have two isogonal conjugates and fit of their altitudes on all the three sides, you get 6 points. So basically what you have here is a 6-point circle. Okay, this circle which passes through these 6 points. Yeah, we can call it a 6-point circle, and most importantly, there are infinitely many such 6-point circles in the triangle, because every choice of point P, and point P was taken completely arbitrary here. So if I choose a different point P, I get a different point Q and get a different 6-point circle. Okay, and now do you see that our 9-point circle is just one such 6-point circle, but because in that case the P and Q are themselves special. So in the case of a 9-point circle configuration, we take, let's say, P will be the orthocenter and Q is the circumcenter. So the 6 feet of the in that case P1, P2, P3 will be the feet of the altitudes of a triangle, and Q1, Q2, Q3 will be the midpoints of the sides. So these 6 points already lie on that circle. In addition, we get 3 special points which are the midpoints of AH, BH, and CH. But of course, in general, something like that will not be true for any isogonal conjugates. Okay, so in a way, you can see that the 9-point circle is a generalization of this 6-point, or not a generalization, a special case of this 6-point circle. Okay, everybody follows this?
Yes, sir.
Okay. So now let us turn to what is the connection of this with barycentric coordinates. So in particular, if I have a point P and Q which are isogonal conjugates, how are their barycentric coordinates connected to each other? So let us try to derive that. So if I have a triangle ABC again, and so now let me consider from point A. Okay, so I will not even draw the remaining two the arms because they are not relevant right now. But let's just say that point P and Q are isogonal conjugates, and we know that, let's say, the barycentric coordinates of P are alpha, beta, gamma. And let me say for now that these are generalized, or a more technical term is unhomogenized barycentric coordinates. Okay, so the term unhomogeneous means that I don't insist that alpha plus beta plus gamma is 1. Okay, so even if the sum alpha plus beta plus gamma is not equal to 1, I can still write the expression P is equal to A alpha plus B beta plus C gamma upon alpha plus beta plus gamma. Okay, so this unhomogenized case is kind of easier to deal with. Okay, because I don't have to worry about the scaling. It's just a scaling factor, right? If I just multiply alpha beta gamma with some suitable constant, I can get their sum to be equal to 1. So I don't want to bother with that every time unless absolutely necessary. Okay. So if this alpha beta gamma are the unhomogenized coordinates of point P, then what are the coordinates of point Q, the barycentric coordinates? Okay, that is the whole question. So for this, we go back to the basic definition of barycentric coordinates. In particular, one interpretation, which is the ratio of the two coordinates. So in this case, for example, because we are considering through point A, let us focus on beta and gamma. So do you agree that basically the ratio of beta is to gamma is nothing but the ratio of those triangles, the areas of those triangles. So beta means the point triangle opposite vertex B. So that is triangle PCA, and for gamma it is triangle PAB. Okay. So whatever is the scaling factor, it doesn't matter, but the ratio of beta and gamma will be this PCA and PAB. Correct? So now, suppose the paracentric coordinates of Q are given as A dash, B dash, C dash. Oh, sorry, I mean alpha dash, beta dash, and gamma dash. Okay. Then in the same way, the paracentric coordinate beta dash and gamma dash will be in the ratio of the area of QCA and QAB. Okay. So if everybody follows this, and also the fact that PQing isogonal conjugates means these angles are again reversed. Like if this is alpha 1, alpha 2, then this is alpha 2, alpha 1. Then based on this information, can you deduce the connection between these two ratios? I'll give you some time to think.
So beta upon gamma is equal to 1 upon beta dash upon gamma dash.
I don't exactly agree, because when you take the areas, right, you need to consider the bases. So base B and C will be somewhere in the picture. At least the expression which I have on my side. Can you just check your calculations once?
Okay, sir.
Okay. So how do we start with this? So we are interested in the areas of these triangles. So which means that if we take the sides small b and small c as the basis, then we are looking at these heights. So same as before, if we drop the altitudes. Okay. So let me do this only for point P to begin with. I'll look at point Q in a moment. So if I consider these points as some P2 and P3, so then the area of triangle PCA is half into the base small b into the length PP2, which is nothing but AP into sine of alpha 2. Okay, and area of PAB will be half into size C into this PP3, which is nothing but AP into sine alpha 1. Okay, so therefore the ratio beta is to gamma, beta upon gamma, which is the ratio of these two terms, will be, so AP will cancel out completely. So it will be simply B into sine alpha 2 upon C into sine alpha 1. Okay, this is beta upon gamma. Then the same thing can be done for Q also. The only thing that will change is alpha 1 and alpha 2.
Yes, sir. It becomes sine alpha 1 upon sine alpha 2.
Right? So beta dash upon gamma dash will be the same thing, but it will be sine alpha upon sine alpha. So the only thing I have to do is I have to eliminate alpha 1 alpha 2 completely from this. So if I just multiply these two together, what I get is beta upon gamma into beta dash upon gamma dash will be equal to B square upon C square. Right?
Yes, sir.
And so symmetrically, I could do the same thing on all the three sides. So ultimately, what this means is the ratio alpha into alpha dash. So if I multiply the paracentric coordinates of P and Q, so these three terms are going to be equal in ratio to A square, B square, and C square. Right? So in other words, if I just rearrange this, what it means that alpha dash, beta dash, gamma dash can be set as A square upon alpha, B square upon beta, and C square upon gamma. Okay, and one of the interesting thing you'll see here is that by design, basically when you say from P you get the isogonal conjugate as Q. If you do the same thing starting from Q, you are supposed to return back to P, right? So you'll see that this expression has that property that basically starting from alpha, beta, gamma, I got this pair A square upon alpha, B square upon beta, C square upon gamma, which is the coordinates of its isogonal conjugate. Now, if I apply the same transformation to this, I will get back alpha, beta, gamma. Better. So A square upon alpha is nothing but alpha. Okay. So basically, the same formula applied to this is giving me back to original expression, just as a sort of confirmation that this formula seems to be right. Okay. So if P has this paracentric coordinate, again unhomogenized, alpha, beta, gamma, then Q has the coordinates A square upon alpha, B square upon beta, and C square upon gamma. Okay. And if you go back to last time's lecture, we had derived the paracentric coordinates of the incenter I. Do you remember what are the unhomogeneous coordinates of incenter?
So A upon 2s, B upon 2s, C upon 2s.
Right. So those are the homogeneous ones where the sum was equal to 1. But if I remove that condition that I insist the sum to be equal to 1, I can drop the 2s from the denominator, right? So I can simply write A comma B comma C. And so now do you see that under this formula it makes sense that I is its own isogonal conjugate?
Yes.
Because the isogonal conjugate of A is nothing but A square upon A, so which is A again. Okay. And I think the same thing will be true for the other excenters also. So I1, even I1 has the same property, etc. So again, all of this is sort of independent confirmation that our formula seem to be correct. Okay, and so as an exercise, because O and H are isogonal conjugates of each other, I would suggest you to derive O and H paracentric coordinates independently and check if they are following this property. That basically the product of those coordinates should be equal to A square, B square, and C square. Okay, so all of this is good. So one of the last things I want to cover in complex numbers, and as I said, I would encourage you to read the Ivan Chen book for a lot more details and many practice problems also. But one last thing that I would like to cover is actually two things. But so the first thing is, so are there any points which will not have any isogonal conjugates? That was one question I asked last time. So what do you think? Will it be the case that every point in the plane has an isogonal conjugate, or could it be that some point will not have a conjugate? So when we say the point doesn't have an isogonal conjugate, what will happen? So if I start with a triangle uh, and I take some point P, okay. Now I'm considering the rays which are the reflection in the angle bisector. So starting with AP, I might get a ray AP1. Okay. Similarly, I might get a ray BP2 and CP3. So the question is, could it happen that these three rays are not concurrent? They don't intersect in a point. So for example, I mean in this diagram, it seems that if I take the point P in the interior, they will have to intersect. And if they intersect, then we know whatever we derived earlier, they will be concurrent. But maybe if I take the point P outside the triangle, what if these three rays are parallel? Then these rays may not intersect at all. In a way, you can say they intersect at the point at infinity, but in the normal finite geometry plane, there will be no isogonal conjugate of such a point. So can you figure out what is the condition on point P for which these three rays will end up being parallel? Okay, so if you want to figure that out, as I said, the point P most likely will have to be outside the triangle. So because we might be dealing with negative angles and things like that. So let us put everything in terms of directed angles, okay, just for clarity. So the idea is that, and here when we say these two angles are equal, we are not really making any statement about the angle, the signs of the angles, the positive or negative magnitude. So instead of just saying the angles are equal, specifically in terms of directed angles, what I want to say is angle BAP is equal to angle P1AC. Okay, so in other words, I'm assigning directions to these equalities. So basically, I want to I want to formalize the idea that if I'm rotating clockwise from starting from side AB, then I want to rotate anti-clockwise from AC. Okay, so that one way to formalize that is the sum is equal. So here, because I preserved the order, both are anti-clockwise. Therefore, I am saying they're equal. Another way of writing the same thing could be BAP plus angle CAP1 equal to 0. So in both cases, the starting is the sides of the triangle and we are ending at the internal points. But in this case, the sum is 0. So obviously, these are both equivalent statements, right? So either of them is sufficient to say that this P1 and P are symmetric with respect to the angle bisector. So if I put it in these terms, what do I get? And let me now draw the diagram because as I already said, point P needs to be outside the triangle. So suppose I take the point P somewhere over here. And so let us say again let P1 and P2 be the and look at, and in this diagram it seems almost like they are parallel to each other. So certainly seems to be plausible that for some choice of the point P, these rays could be parallel. Okay. So suppose I start with the assumption that these two rays are parallel. So let us say it is given that the lines BP2 and BP1 are parallel. Then what can I deduce? So in general, when you have any two parallel lines, right? In terms of directed angles, what we can say, and always remember, going back to the original definition of directed angles, they are always between two lines. So in a way, if I call this line M1 and M2, and if M1 and M2 are parallel, then the directed angle between line L comma M1 will be equal to the directed angle of the line L with M2. Does that make sense?
Yes.
Okay. And because we don't use this notation of lines, we often refer to the points, but always keep this in the back of your mind that directed angles are always between lines. So therefore, I mean, if I just choose any points over here, A, B, C, D, E, then the same thing I would write in the way. So instead of writing L comma M1, I would refer to line AB. So this would be and directed angle ABC equal to directed angle ADE, for example. But most importantly, the choice of points C and E. I mean, this statement we all know is true in the normal angles also. But even if let's say point C happen to lie on the other side of this, so if let's say point C lies over here, then also in the directed sense this statement is still true. In the normal angles sense this will not be true. But for directed angles this is still true. Okay? So just keep that in mind. So in the same sense, here the lines which are given parallel to us are these two lines. So if we consider line AB as the transversal, then what is the statement I can say in the directed sense? That the angle which line AB makes with AP1. So basically the angle BAP1 is equal to directed angle ABP2. So in this diagram, it seems like obviously this statement is true because it's true in the normal angle sense. But the important thing is we are writing it this is a directed domain. So I mean, suppose the point P could be located somewhere else, then I mean these angles might flip. Like they might become supplementary in the normal angles, but in the directed angles, everything is taken care of. Okay, so BAP1 is equal to ABP2. Now, applying this the way we define isogonal conjugates, this formula, how do we convert this BAP1 and ABP2 into angles around point P? So angle ABP2 is the same as angle PBC as per this definition. So I can substitute this with angle, directed angle PBC. And what about BAP1? I can say BAP1 is the same as angle
Yes.
PAC, correct? So what are we getting? Directed angle PAC is equal to directed angle PBC. Do you remember what is this about? Forget it, your directed angles. If this happens in the normal angles, if PAC equal to PBC, what can you say?
P, A, B, C are concentric.
They are concyclic, and importantly, the order of the point doesn't matter. When you are talking about directed angles, regardless of what is the order, this will imply that the points are concyclic. Okay. So in other words, what is the locus of all points which don't have an isogonal conjugate?
Circumcircle of.
The circumcircle of the triangle ABC. Okay. Okay. So any point on the circumcircle, if you start with that point P, these rays or the reflected rays will turn out to be all parallel. So therefore, there is no isogonal conjugate. But hang on, that is kind of strange because we just found a formula for the isogonal conjugate. So if my starting point has a barycentric coordinate, I can apply this formula and I'll get the coordinate for the this conjugate, right? Then what will go wrong? Why can't I apply the same thing to the circumcircle? Obviously, if let's say let point P belong to the circumcircle and let it have the paracentric coordinates alpha, beta, gamma, unhomogenized, of course. Then and so if P has a paracentric isogonal conjugate, if Q is the isogonal conjugate of P, then Q has the paracentric coordinates a square upon alpha, b square upon beta, c square upon gamma, right?
Yes.
So then what's happening? So how can this point which does not exist have a barycentric coordinate? There is some paradox here.
Sir, alpha or beta or gamma becomes 0. So we can't divide.
If alpha, beta, or gamma, any of them becomes 0, that is true, we cannot define. But when does that happen? When if alpha is 0, what does that mean? The point lies on the side BC, right? That is the only case when alpha becomes 0.
Yes.
So points on circumcircle anyway, I mean, let's say, okay, let's say ignore the vertices. Okay, vertices may pose some problem. But any point other than vertices which lies on the circumcircle, then alpha, beta, gamma are not 0. Then what can go wrong? Okay, so we need to think about this fundamental question that any point P in the plane, has a barycentric coordinate. I mean, let me not draw the double arrow. If I start with any point P in the plane, I can get a triplet alpha, beta, gamma based on the ratio of the those three triangles. Okay, I can plot these three triangles. I can take the ratio that is alpha, beta, gamma. Is the converse true that if I take any triplet of numbers, real numbers alpha, beta, gamma, then they will correspond to some point P in the plane? Okay. So suppose these are unhomogeneous. Okay. Even if they are unhomogeneous, I can divide by their sum and I'll get some homogeneous coordinates, right?
Yes.
Okay. So this is the problem. To make this unhomogeneous coordinate into homogeneous, I need to divide by their sum. That is where things can go wrong. So what if their sum is 0? Now I cannot homogenize them at all. There is no way to convert a triplet whose sum is 0 into homogeneous coordinates. There is no constant you can multiply, after which this k alpha, k beta, k gamma, their sum will equal to 1, correct? Such a k cannot exist at all.
So I think it is because the Simpson line.
Simpson line. What is the connection of Simpson line? Maybe Simpson line is connected, but I don't see the connection immediately. But do you see that? So the only triplets in all of RQ, if alpha, beta, gamma is a triplet which belongs to RQ, okay. If the alpha plus beta plus gamma sum is non-zero, then we can find a point P. But if they are such that their sum is 0, then there does not exist any point whose barycentric coordinates are alpha, beta, gamma. Okay, does everybody follow this? So if the sum is 0, then those alpha, beta, gamma cannot be the barycentric coordinates of any point. So that is what is happening here. If I start with the point P which is on the circumcircle, alpha, beta, gamma, I try to construct the coordinates of an isogonal conjugate. but a point which we know from geometry cannot exist. So it forces that the sum is 0. In other words, what we actually found is the equation of the circumcircle. So this condition, a square by alpha plus b square by beta plus c square by gamma equal to 0, is precisely the condition satisfied by all points on the circumcircle. So the equation of the circumcircle is a square by alpha plus b square by beta plus c square by gamma equal to 0. And the reason why this is the equation of the circumcircle is this is precisely the set of all those points for which the isogonal conjugate does not exist. Okay, so this was a very kind of twisted way of coming up with this equation, but I encourage you to try this with pure geometry, because amazingly what this seems to say is something kind of fundamental, right? Because we know alpha, beta, gamma are simply the ratios of those three areas, those triangles. So this is a homework for you. Try to prove this from pure geometry, that if this statement is true, that this is the equation of the circumcircle, then if I take any point on the circumcircle, okay, let P be any point on the circumcircle, then I should be able to prove that, because I can replace alpha, beta, gamma here with those three triangles. There is a factor which is delta, or the area of the triangle ABC itself, but that will cancel out because the RHS is 0 anyway. So therefore, it should be true that A square upon area of BBC plus B square upon area of PCA, and these are directed areas, mind you, so area of PAB. The sum of these is equal to 0. So in this particular example where P is on this arc BC, then this PBC will be negative and these two will be positive. Okay, but in any case, this statement should be true. Okay, so I'll encourage you to try and prove this independently. I think that is where the Simpson line correction comes. Is that what you're saying? I don't know, possibly. But anyway,
Yes.
I'll leave it to you to figure out. In fact, you know what? Even I have not tried this before. I'm thinking, is it easy to finish this off in the next 5-10 minutes? Then we might as well do it right now. Let me think. Maybe we'll just take 5 minutes to think about this. If we can prove this with pure geometry, that would be very nice. Anybody already sees how to prove this? Can you raise your hand? Okay. Okay, then let's try to prove it. It's an interesting statement. So maybe, I mean, I'm just thinking aloud here that first step would be to replace the areas with the heights. And let's say we work with the special case where P lies on this side PC. So we get rid of the directed angles, directed areas, and turn everything into normal area. So in that case, what I want to prove is that, so in normal areas, in unsigned areas, it is enough to show that. So I take A square upon PBC on the other side. So A square upon PBC is equal to B square upon CA. And here, assuming P lies on RBC. By symmetry, the same thing will be true if P lies on the other two arcs. So I think it's enough to prove this case. So if I consider if I drop the altitudes, then by Simpson line, I know these feet of the altitudes are collinear. But I'm interested in the height. So if I call this distance as h1, h2, h3, then I know I can write the areas in terms of h1, h2, h3, right? So PBC is nothing but half AH1. So conveniently, I guess one copy of the side gets cancelled. So A and A square, one copy will go away. So this will be equivalent to half A upon Okay, does this make sense? That it's enough to prove this statement.
Yes, sir.
Okay, now but why is this true? And can we make use of this collinearity in some way? The Simpson line collinearity, is that relevant in any way? Okay, so this is what I'm thinking. Maybe I'll leave it for you to see if this can be worked out. But see, A upon H1 is BC upon H1. So if I call this fit of the altitude D and F, then I can split BC as BD plus BC, right? So the LHS can be written as BD upon H1 plus DC upon H1. Okay. And the purpose of doing this is that now if you look at, for example, DC upon H1, then I have a right angle triangle over here, right? CDP. In that, DC upon H1 is nothing but this particular, in terms of trigonometry, I could write it as cot of this angle, okay? Cot of this angle DCP. Okay. So DC upon H1 can be written as cot of DCP. And the idea is that this angle DCP can be found in other places. Because we have cyclic quadrilaterals, we can transfer these angles in many other places. In particular, I am thinking if I similarly join AP, then this angle is equal to this angle. So then this same term will also turn out on this side. So basically, by similar triangles also we can say, because these two angles are equal, triangle DCP will be similar to which triangle? Triangle FAP, correct? So therefore, this DC upon H1, DC upon DP will be equal to FA upon FP. So like that, term by term, something on the LHS will be equal to something on the RHS, etc. Okay, that, at least broadly speaking, that is what I'm thinking. But anyway, I think I'll leave it for you to try and see if you can complete this detail. Okay. But anyway, I hope you followed what we did earlier. So, I mean, this equation of the circumcircle turning out to be something like this. And of course, if you want, you can clear the denominator. If I multiply everything by alpha, beta, gamma, I'll get everything in the numerator. That is also fine. Okay, so this was the equation of circumcircle. So the last thing which I want to show in terms of paracentric coordinates, so I had plotted one GeoGebra file. Okay, so I have plotted this file in 3D geometry to illustrate how barycentric coordinates behave. So what I've done here is, so the triangle ABC which you see on the top right, that is the reference triangle, and this point P is any point inside that triangle. Okay, and as that point P moves, I want to plot the barycentric coordinates of that point P, which is alpha, beta, gamma, right? So it's a triplet of numbers. So that triplet of numbers can be plotted in the 3D geometry space. So that's what I've done here. So here this red, green, blue lines are the alpha, beta, gamma axis if you want. Okay. So basically, as the point P, let's say if I take the point P, yeah. So if I take the point P, so if I take the point P and put it at the vertex A, then you see in this bottom left representation, this the red point L, which is the barycentric coordinate triplet, that its coordinate becomes 1, 0, 0. So you can check the coordinate of this point L. L. Okay, so on the left side you can see this L. Its coordinates are being plotted at in the real time, and so I mean these are homogeneous coordinates. So their sum will always be equal to 1. So when I put the point P very close to A, you will see that its homogeneous coordinates are almost 1, 0, 0. Then if I move it to location B, it's 0, 1, 0 and 0, 0, 1. Okay, so in that way, I'm plotting this. And in fact, any point outside is also represented. So everything is happening in this plane. So this plane, if you see, this is the plane whose equation is alpha plus beta plus gamma equal to 1. So therefore, this point L is confined to this plane, alpha plus beta plus gamma equal to 1. But every point on this plane has a barycentric coordinate. In particular, so this is a 9-point circle. This ABC is the 9-point circle. So if I put the point P along this 9-point circle, what happens to the barycentric coordinate? So if I start trailing this point, okay, and if I just move this point around on this circle, it's hard to do without a mouse, but I can just try to do it roughly. So can you see what is the shape that the barycentric coordinate seems to be plotting?
An ellipse.
An ellipse. It's not a circle. Okay, very important. So the thing is, if point P moves on a line, then the barycentric coordinate also moves on a line. So so a line remains a line, but a circle becomes an ellipse. Okay, this is a very important difference. But so the important point about the line remaining a line, we can illustrate in a different way. This ellipse also has an equation in 3D, which I mean we are not really equipped to do it at this point, but we will study this in the 11th standard when you do conics more formally. So at that point, you can sort of revisit this idea that how any general circle in the plane, its barycentric coordinate are nothing but an ellipse in 3D space. So anyway, I'll share this GeoGebra file with you if you want. You can just play around with it a bit more. One important thing you realize. forgot how to clear the trace. Anyway. So actually what I wanted to illustrate was this point P when it's the centroid. At that point, so I'm just roughly putting it at the centroid, I don't know. But if you see the barycentric coordinates over here, it's almost 1 by 3, 1 by 3, 1 by 3. So that centroid is the only point which is sort of invariant in that sense, that any triangle you take, the centroid is always 1 by 3, 1 by 3, 1 by 3. Any other special point like the incenter, etc., we know that the barycentric coordinate itself is a function of the sides ABC. So numerically that barycentric coordinate is not a constant for any other point, but for the centroid it's always 1 by 3, 1 by 3. So actually this idea that a line remains a line, if I want to illustrate more formally. So basically what I want to say is that if let's say I have 3 points P1, P2, P3, and they have some barycentric coordinates alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2, and alpha 3, beta 3, gamma 3. So the claim is, and I'm not really proved this formally, but I'll leave for you to do. It can be done using section formula. The claim is that these 3 points are collinear if these 3 triplets are collinear in the 3D space. Okay. So for these 3 points to be collinear in a triangle ABC, the if and only condition is their corresponding barycentric coordinates. If I interpret as the coordinates of a 3D point, then those 3 3D points are collinear themselves in this RQ. And you may already be knowing this, or if not, you will study this eventually, that the condition for such 3 coordinates being collinear is that the determinant is 0. Okay. So if I construct a determinant, this determinant is 0 is the condition. So in other words, for the same thing is true for the 3 points. So any 3 points whose barycentric coordinates are given, if you evaluate this determinant, you will figure out what is the whether these points are collinear or not. In fact, going further, there is a connection between the area of the triangle. So this area is equal to this determinant. I forgot some constant k. I think this constant is nothing but the area of the triangle ABC or something like that. But anyway, so this determinant is proportional to the area of triangle A, this P1. So therefore, obviously, if these points are collinear, then the area is 0, and so this determinant is also 0. Okay, but anyway, these are kind of bit more advanced points, so just referring them here in case you are interested. Okay, with that, I want to at least for now stop talking about complex numbers. As I said, actually, the reason why I started talking about complex numbers is that I wanted to divert our attention to polynomials, but sort of one way of introducing the idea was through complex numbers. So anyway, I thought we'll cover these points. So now I want to switch gears and go into algebra. So we finished two big topics so far. So one was geometry, then we did several examples in combinatorics. So now I want to focus our attention on algebra. So within algebra, the topics of interest for us are things like polynomials, inequalities, sequences and series. What else? Complex numbers, like roots of unity, those kinds of things. So we'll start with polynomials. And like broadly speaking, I should say when I started doing this lecture series for MPI, that was the first time I started to teach algebra formally. Until then, I mean, whatever lectures I had taken were all in geometry mostly, and sometimes combinatorics. So in a way, I would say even I am a beginner to algebra. I mean, the thing is that in geometry and combinatorics, most of the times, any question which I give you, like solve this problem, and I am able to tell the solution because most of the time I have derived the solution myself. So I know where the motivation comes from, because that's the most important part of this training. See, just giving you the solution will not help you if I don't also explain how you are supposed to come up with that solution in the exam. Okay, so thinking of those ideas in real time is very the most important part of this training. And there I was very well equipped in geometry and combinatorics from my experience, because I could work out what is the motivation. Unfortunately, in algebra, many times I myself have to look up the solution somewhere. I'm not able to solve the problem myself. So I can read the solution, I can relay that solution to you, but that will be only partially valuable. More importantly, why you should think of that solution, sometimes I may not be able to communicate, but at least wherever possible, we'll try to motivate this. But to keep this at the back of your mind also, when you are solving problems, just don't stop at the point where you solve the problem and you move on. Think about why you're supposed to think of this idea in the first place, because then you might think of the same thing in a different problem, etc. But anyway, I mean, to the extent that I can teach this topic, let us proceed. So, polynomials, formally, as I said a few lectures ago, there is a whole field of abstract algebra under which we put various sets into different categories based on their complexity. So, we talked about things such as groups, rings, and fields. So, in that kind of classification, the polynomial happens to be in the category called a ring. The polynomials are examples of rings. And again, in the interest of time, I don't want to dive into the full theory of what do rings comprise of. But very simply speaking, what this means is that addition and multiplication are defined, and addition is a full commutative group. In other words, basically, when I say a group, what that means is things such as associative properties through. There exists an identity such that anything plus 0 is A, and for every A, there exists a dash such that A plus A dash equal to 0. So, existence of identity, existence of inverse. In the normal group definition, the commutative law is not added, but when I say commutative group, this additional property is added to the back that A plus B equal to B plus A. Okay. So in terms of addition, everything happens very nicely. In terms of multiplication, things are partially good. Okay, they are not totally good. So the thing is, in multiplication, inverse is not guaranteed. So still there exists an identity. So A into 1 equal to 1 into A, but there may not exist inverse. So for every A, there may not exist inverse such that A into A inverse is equal to 1. So this is the key idea, this non-existence of the inverse, which differentiates the rings from the fields. Okay, and so intuitively, I think this motivation is enough to indicate why objects such as integers and polynomials, they are classified as rings, because again in integers the same thing happens. Addition is fully workable with commutativity and everything, but multiplication, inverses don't exist in integers, right? 5 inverse of 5 is not an integer. In the same way, polynomial x is a polynomial, but 1 upon x is not a polynomial. So very intuitively we get this idea. Okay, but the similarity does not end there. I mean, the reason why I'm talking about this is that broadly speaking, there is a whole field of properties which are true in rings, which are also true for integers and polynomials. And you may be surprised to know that when we study number theory, we study a lot of properties of integers, and we think that they are true because integers have this property. The truth is that they are true because rings have this property. Something as simple as the prime factorization. So we know that any integer n can be factorized into primes. And we call this the fundamental theorem of arithmetic and all those things. Turns out that that statement is true for objects in some rings also. So even the rings have a concept of factorization. And in a way, we know polynomials have the same property, right? I know that a polynomial like x square minus 1 can be factorized into x minus 1, x plus 1. And there is a certain sense in which these can be called primes, because why are we called them primes? Because they cannot be factorized further, something like that. So again, I'm not formally developing these concepts in full, but I'm just indicating how a lot of similarities between integers and polynomials are there, because in fact they are both special cases of a much larger structure called a ring. Okay, things like GCD and LCM are well defined in integers as well as polynomials, because they are both examples of rings. and so on and so forth. So really, I mean, sort of motivating you to study this broader algebraic structure of a ring and everything that you can do with it. Okay. But so now let us focus on only polynomials for now. So a polynomial in general is what? And here, like from the definition itself, there are some tricky things which students need to be like pay special attention to. So when I say a polynomial, typically we say a polynomial over some set. Let's say I'm talking about integers, so polynomial over z, which means that I'm talking about polynomials whose coefficients are integers. But I mean that is a lot of words, so we need to say what is the coefficient, etc. Very simply speaking, you can just think of polynomial as nothing but a finite tuple of elements of z. Okay, so it's just a finite tuple means an ordered set of numbers. So if I am considering the polynomial x square plus 2x plus 5, this is one way of writing it. I could simply write 1 comma 2 comma 5. Okay, this is a perfectly valid way of showing the polynomial also. And the importance of this form is that somewhere we feel here when I write it in this form that x is also part of the definition. But understand that x is nothing but a placeholder. Okay? When I say px is equal to this, I'm just instead of writing the coefficients like 1 comma 2 comma 5, I'm just found a different way of writing those. So this is simply a part of the representation. And sometimes some authors to make this point use capital X. Okay, so you might often find in books like it is written capital X square plus 2 capital X plus 5. Because the key thing which we want to drill into your mind is that when I'm just writing this equation, I'm nowhere saying that I'm multiplying 1 with x square, then multiplying 2 with x, and then 5, and then I'm adding all of those things. So all of those things are not part of the definition at all. This is just a sort of a placeholder that I want to keep some objects. So instead of keeping them in a set like this, I've decided to keep them along a numerous power series of x square. So that is the definition of a polynomial. Then we come to what we call the evaluation of a polynomial. So evaluation of the polynomial at some special value, let's say x equal to 2. So this is the point where we actually substitute a value and we get a numerical answer. So p of x as an expression is not an integer. Okay? P of x belongs to a special set which is a polynomial of all polynomials over integers. Okay, so this p square bracket z is the notation we typically use to denote the set of all polynomials with integer coefficients. So p of x is a member of this set, not a integer. Only when I substitute some special value in x, like x equal to 2, I get some numerical value of p of 2, which is, let's say here what is the answer to 4 plus 4, 13. So then this number is a member of the integers. Okay, so make sure in your mind is clear distinction between the polynomial and its evaluation. They are not the same thing. And this point crucially becomes critical in some questions, like you might get a question like I don't know. So when I say, let's say I have two polynomials p of x and q of x. Okay. Then when I say p of x plus q of x is equal to r of x, this is a polynomial equation, not an equation in integers. Okay. So the polynomial p of x is being added to the polynomial q of x to get a new polynomial r of x. But if I put some values, I may get some like integer expression, like some 2 plus 5 equal to 8 or 7 or anything like that. But this is a polynomial equation, not an integer equation. I'm trying to think of some concrete example why this sort of separation matters. I should have thought of this before the lecture, but just give me a minute. There is one very interesting example in terms of number theory. Uh, okay, yeah, something like this. This is very interesting. So, so consider the number 2. Okay. So 2 as a number of integers, which is fine. But I could also think of a polynomial q of x, which is equal to 2. So this is a constant polynomial. This, while writing on paper, I'll still write it as 2. But now this 2 represents a polynomial. It is not an integer. Okay. So when I say a statement such as, so is it true? I'll ask you a question. Is it true that 2 divides x into x plus 1?
Yes, sir.
So the answer is yes, if we are talking about 2 as the integer and x into x plus 1 as some numerical value in integers. But if these were polynomials, so the polynomial 2 is not a factor of x into x plus 1. Do you realize the difference? X into x plus 1 has factors. The factors of x into x plus 1 are the polynomial x and the polynomial x plus 1. 2 is not a factor of this in the polynomial domain. But it just happens that when you substitute new numbers in the value of x, then in the integers, the number 2 happens to be a factor of x into x plus 1. Are you seeing the subtle difference?
Yes, sir.
So in the polynomial domain also, we can say the polynomial px divides polynomial qx. This is a perfectly valid statement if p of x can be written as p of x into some e of x. Okay, so if the polynomial q of x can be separated into 2 polynomial factors, then something like this is true. So for example, it's perfectly valid to say x plus 1 divides x square plus 2x plus 1, because x square plus 2x plus 1 gets factorized into this. Or in the example which we are talking about, x plus 1 is certainly a factor of x into x plus 1 in the polynomial domain. But in the polynomial domain, 2 is not a factor of x into x plus 1. It just happens to be the case that if I substitute integers, then this is true if x is an integer and 2 is an integer. Okay, so just keep this distinction in your mind. The polynomial domain, which is denoted by p of z, and when you substitute some numerical value in that x, you get a real number or integer depending on the domain. Anyway, I don't want to stress on this point too much, but I hope you get the idea. So then, what are some properties of polynomials? I think we all know how to add and multiply polynomials, so I won't spend time in that. Probably the most important connections come from the relations of the coefficients and roots. Actually, before that, division algorithm. Yeah. So division algorithm is simply, so if p of x and q of x are polynomials, and for now I'm taking the polynomials in the real domain, but all of these things can be extended to rationals, reals, complex numbers. Sorry, so I'm taking integer domain. Okay, p and q are, or let me use a and b. Okay, just that, and b is non-zero. So again, when I say bx is non-zero, what is the meaning of this statement? I am not saying b of x as a value can never be 0. There could be some special integer for which bx can be 0. but b of x is not identical to the zero polynomial. That is what this statement means. Okay, so this point will keep coming back. B of x not equal to 0 does not mean that some special value of x, b of x is non-zero. 0 here refers to the zero polynomial. Okay. 0 is also polynomial of undefined degree. Okay. All other polynomials have a finite degree. So, like constant polynomial has degree 0, x has degree 1, etc. 0 is the polynomial which is undefined. Okay. So then there exists polynomials qx and rx, unique polynomials qx and rx, such that p of x is equal to q of x b of x plus r of x, and the degree of r is less than degree of b. Well, degree I did not formally define, but I hope everybody understand. Degree is the power of the largest non-zero constant or non-zero power of x. So this is the division algorithm for polynomials. So if you have any two polynomials and the divisor is non-zero, then we can divide one with the other and get a unique remainder and coefficient. Just give me a minute because I'm thinking there's some nuances to this. Yeah, I guess the most important thing I have to specify here is that the q of x and r of x are also in the same domain. So the same pz domain is being used here, only then this uniqueness is guaranteed. If you allow, I mean, if you take some example like where the coefficient, the quotient and remainder are polynomials in rational numbers, for example, then there could be multiple ways of dividing the same polynomials. So, for example, let's say if I have to divide x square plus 1 by x, the x square plus 1 is nothing but x times x plus 1. So here, this is my dividend, this is my divisor, this is my quotient, and this is my remainder. So in this case, the quotient and remainder are guaranteed to be unique because everything is in terms of integers. But I mean, there could be examples where I'll have to construct an example specifically. I don't remember, but maybe I'll leave this as exercise for you. Try and show one counter example. If I allow the coefficient and the quotient and remainder to be polynomials beyond the integers, then I could come up with some counter example where I mean they will still exist but will not be unique. Okay, so that is one fine point to be made there. So sort of a consequence of this is some statements such as the remainder theorem. What the remainder theorem says is that basically it turns out that if you have any polynomial p of x, right? So if p of x is some polynomial in integers, and you substitute some value in x, so let's say I divide p of x with the divisor x minus a. So q of x into x minus a with some remainder r of x. Okay. So now here this x minus a being the divisor. So what by the division algorithm, what we know is that the degree of the remainder is smaller than the degree of your divisor. So if your divisor is of degree 1, then the remainder is going to be some constant number. So this r of x is going to be essentially some constant number. Let's say we are talking in z. So r of x will be some constant in z. So or rather, let me not abuse the notation. When I say constant Again, it's a constant polynomial. So the r of x, if let's say r of x equal to 1, this is a constant polynomial 1. This is not in z. It's only a polynomial whose degree is 1. So I should not make that mistake. But so now in this expression, now if I evaluate this, so this is a polynomial equation. But now if I substitute x equal to a, then I'm converting this polynomial equation into an integer equation. And in that integer domain, what will happen? P of a is equal to P of a times a minus a plus whatever this constant was. And then obviously because this term is 0, what I get is that P of a is equal to r of a. Now this is the equation in integers. So what this means is the numerical value of that coefficient happens to be equal to P of a. Okay. So what the remainder theorem says is that the remainder on dividing any polynomial P of x with x minus a is P of a. Okay. So the remainder of dividing P of x with x minus a is P of. So, but when I make a statement like this, understand that this P of a, although it's an integer, I'm converting that integer back into a polynomial of degree 1. So there is a sort of tricky back and forth conversion between the integers and the polynomials or integers. But anyway, I think I've already spoken about this point so many times that henceforth I will not keep on referring to it. I trust that by intuition you know that when I'm writing P of a, when do I mean that to be an integer and when do I mean that to be a polynomial of degree 1 or whatever degree I want. So that's the remainder theorem. Okay, so then the most important point is about the roots and the coefficients. So what are the values at which that polynomial evaluates to 0? And what is the connection of those roots with the coefficient? So can you raise your hand if you already know these properties, what are called Vieta's relations, that the coefficients are a sum of 1 at a time, 2 at a time. Okay, I think most of you know these things. So okay, so I will not spend time on stating that, but there are some further implications of those statements. Okay, so I'll talk about that in more detail. So for those who may not know this, you can look it up. It's called Vieta's relations, and they stem from the simple fact that if the polynomial now let's do everything in complex numbers. Okay, so far I was talking about integers, but now let us consider all polynomials in complex numbers because we know that we know, but we have not proved that complex polynomials have their entire roots in complex numbers. Again, that is a sort of a corollary of some statement from field theory, which we are not equipped to study. So if Px is a polynomial in complex domain, and if the coefficients of this are some x raised to n plus a1, an minus 1, x raised to n minus 1 plus etc. And then if the roots of, if P of x has the roots alpha 1, alpha 2, alpha n, then I could also write this as x minus alpha 1, x minus alpha 2, etc. Then if I expand this second bracket completely and I equate it term by term with the first one, then that is what gives me this Vieta's relation. So basically an minus 1 is the sum of all the roots minus of that. An minus 2 is the sum of the pair at a time product, etc. Okay, everything. And the final term a0 is the sum of the a alpha 1, alpha 2, alpha n. So basically this is simply a simple product of all the terms. So I'm just writing sigma for consistency, but it has only one term and into minus 1 raised to n. So I want to focus on these what are called the elementary symmetric polynomials. Okay, so these are called elementary symmetric polynomials. Okay. So I want to sort of unpack what is the meaning of each word in this statement. So we'll start with some small examples. So let's say I'm talking of only degree 3. Okay, so let's say P of x is at degree 3. Degree of P of x. Okay, So in that case, let's say I might have three roots, alpha 1, alpha 2, alpha 3. Okay. So let's say the roots are alpha 1, alpha 2, alpha 3. Then these expression which I'll create, right? So the first expression, and typically we use the letter sigma 1. So sigma 1 is the sum of all one at a time. Sigma 2 refers to the product two at a time and added together. And sigma 3 is alpha 1, alpha 2, alpha 3. Okay. So the thing is, these are themselves polynomials. They are called what? Multivariate polynomials. So sigma 1 is a multivariate polynomial of alpha 1, alpha 2, alpha 3, etc. So each of them is a multivariate polynomial of alpha 1, alpha 2, alpha. So that is why we call them polynomials. Then they are symmetric. So why are they symmetric? Because if I exchange any two of these alpha, so if I exchange alpha 1 and alpha 3, the value of this expression does not change. Okay, any two of them I can swap. I can reorder all the these polynomials, all these alpha 1, alpha 2, alpha n in any way, but the expression remains the same. Okay, and this property is true for all of these sigma 1, sigma 2, sigma 3. That is why we call them symmetric. Do you know why they are called elementary? Anybody? So the reason why they are called elementary is the statement that every symmetric polynomial over alpha 1, alpha 2, alpha 3 can be expressed in terms of sigma 1, sigma 2, sigma 3. So this is what this makes it elementary. It's almost like these are the building blocks, like the atoms, which can be used to construct any other symmetric polynomial. So for example, polynomials such as alpha 1 square plus alpha 2 square plus alpha 3 square. Do you see how to represent this in terms of sigma 1, sigma 2, sigma 3?
Sigma 1 the whole square minus 2 sigma 1 sigma 2.
Right? This is sigma 1 square minus sigma 2, right? 2 sigma 2, correct?
Yes.
Okay. So do you see how? So the important thing is that this is the symmetric polynomial. This also has the same property that if you swap the alpha 1, alpha 2 or any of them, you reorder them in any way, the polynomial remains unchanged. So that's why this is a symmetric polynomial. And what this statement says is that it's always guaranteed that you can write this polynomial in terms of sigma 1, sigma 2, sigma 3. That is what makes these polynomials elementary. Okay. And of course, all of this I'm doing with a special case of three numbers, alpha 1, alpha 2, alpha 3. But the same theory extends for any, like even if you have n variables, alpha 1, alpha 2, alpha n, you get sigma 1, sigma 2 up to sigma n. Okay, so you get the elementary symmetric polynomials of degree n. So of degree n in general. Here we are talking about n equal to 3. Okay, so that is the broader relevance of these expressions. And like this often comes up in, you might get questions which are like simultaneous equations, right? You might solve the system of equations, some A, B, C are given, and you want to solve them. If the given equations are all symmetric, often you can convert everything into the sigma 1, sigma 2, sigma 3, because once you know the values of sigma 1, sigma 2, sigma 3, you can construct a polynomial with those coefficients, and the roots of that polynomial will be your alpha 1, alpha 2, alpha 3. Right? Does that make sense? So suppose some question is given where suppose solve this system of equations, solve, and of course they will not give in terms of alpha 1, alpha 2, alpha 3. Suppose they give solve some equation system. Like suppose x plus y plus z equal to something, x square plus y square plus z square equal to something, x cube plus y cube plus z cube equal to something. Okay. Suppose you are asked to solve this system of equations. What can you do? And let's take some number. Let's say x equal to 1, y equal to 2, z equal to 3. So then this is 6. This is 1 plus 4, 9 plus 14. And this is 1 plus 4, 9, 36. Okay, so solve these equations where given, let's say, all x, y, z are reals. So what will you do?
So sigma 1 is equal to 16 sigma 1 the whole square minus 2 sigma 2 is equal to 14.
Correct. So here, by the way, this sigma 1, sigma 2, sigma 3 are being defined over x, y, z, right? So basically, sigma 1 is x plus y plus z, sigma 2 is x, y plus y, z plus zx, and sigma 3 is x, y, z. So in the same way, you can represent x
So
cube plus
sigma
y.
1 the whole cube minus 3 sigma 1 sigma 2 plus 3 sigma 3.
I'm just writing what you're saying. I hope somebody is going to check this. But basically, you can just expand x plus y plus z whole cube, and you can easily factorize it and get the expression. Okay. Okay. So now what you can do here is that suppose I
These are regular lectures.
sorry,
So we have studied this in our regular lecture.
you have studied this. Okay, that's good. Okay. Then I will skip all of this. So basically now then you know how to apply this in actual problems. Okay. So I'll skip over this one part. Then okay, maybe next time there are some one or two other properties about symmetric polynomials which I'm missing right now, but I'll have to revise them and I'll talk about that next time. Okay. So then moving on to the next point in polynomials. So you need to consider some special cases when a root may exist or root may not exist, and these kind of problems are very typical in Olympiad. So so there is one. I think, do you already know PRRT, possible rational root theorem?
Yes.
Yes, sir.
Okay. Then do you know this Eisenstein's criterion?
No, sir.
No, sir.
Okay, so we studied that. So again, maybe PRRT, in case anybody is not recalling, it is simply about if you have a polynomial with integer coefficients, and in fact you can extend that to rational coefficients also. Then when does that polynomial have a root or not? So what are the possible numerator and denominator for that rational root? So you can simply in terms of divisibility, you can work out that I think the denominator has to divide the leading coefficient and vice versa, something like that. Okay, so anyway, you know that. So Eisenstein's criterion is a special theorem which deals with polynomials with integer coefficients. So Eisenstein's criterion. And I think we are going to devote a good amount of next lecture in deriving this property. Okay, but let me just state it here. So let Px be a polynomial of integer coefficients. So the criterion is about irreducibility of polynomials. About irreducibility. Irreducibility of polynomials. So what is it? What this means is that does a given polynomial can have factors, non-trivial factors in Z. So a polynomial such as x square minus 5x plus 6 has non-trivial factors such as x minus 2 and x plus 3. But a polynomial such as x square plus 5x plus 2, let's say, there is no way to factorize this. We know how to factorize this in real numbers or maybe complex numbers, depending on what are the roots. But this polynomial has no factors in the integer domain. So there are no integer coefficient factors of this, non-trivial of course. You can of course write this as 1 into the polynomial itself, but non-trivial factors. So this special case talks about some polynomials which, if they satisfy some special conditions, then we can say that that polynomial is irreducible. That is what Eisenstein's criterion is about. So the conditions are, let P be a prime. Actually, I need to write the polynomial in full. So let P of x be equal to some x is to n plus a minus 1 x. Okay. Suppose this is the polynomial, and so these all ai's are all integers, such that So the property is that P divides all the P divides A0. So P divides the first P divides the smallest coefficient A0. P divides A1, P divides A2, etc. So P divides all the coefficients, but not the last one. Okay. And in addition, P square does not divide A0. So if these statements are true, then P of x is irreducible over Z. Actually, not. I don't remember whether this statement. Just give me 1 minute. I'll check this. Okay. Actually, I made a mistake. So yeah, actually there is a coefficient an also here. So the condition is that P divides A0, A1, A2, everything up to an minus 1, but not an. Actually, I don't know what's the difference, but anyway, I'm just writing it as it is for now. Okay, so some prime exists which divides all the coefficients A0, A1 up to an minus 1, but not an. And this additional condition that A0 should not be a double multiple of P. So P square should not divide A0. If all of this is true, then Px is not reducible over Z. In other words, Px will not have any non-trivial factors in integers. So anyway, we are almost out of time today, but I'll encourage you to try and prove this. The proof is by contradiction, that if Px is equal to some Qx into Rx, and then you can try to work out term by term how the coefficients multiply together and things like that. So anyway, I'll leave this as exercise for you to try next time. And actually there is a more, so what I've given here is a special case. Actual Eisenstein criteria is a bit more general. So I'll also have to revise that, and we'll do that next time. Anything else? Okay, anyway, we are out of time, so I won't have to cover anything else today. Okay, I think that's all for today. Thank you. Bye.
Thank you, sir. Bye, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Bye.